The last class we were talking about the structure and properties of certain construction materials. We started off with cement concrete and we were engaged in a discussion on the structure of asphalt concrete, which is basically a mixture of bitumen plus the aggregate, right. And we were looking at what are the different techniques with which you can lower the viscosity of the asphalt to enable its mixing with the aggregates, placement and consolidation. So, the three common techniques is to heat the asphalt or to prepare an emulsion or to prepare a cutback, which is basically the solution of the asphalt in an organic solvent. Okay. Now, as I was talking about earlier, asphalt has a major tendency to be affected greatly by temperature. Just like any other polymer, the properties of asphalt concrete are affected tremendously by temperature. So, as a result, we need to look at safe working temperatures or ideal working temperatures with this material. Right? We know that when we design a pavement for service in a particular location, there are specific ranges of temperatures to which this location will be subjected to, right. And we need to ensure that the kind of material that we select, the asphalt that we select, is suitable for this environment. Because if you look at the viscosity versus temperature plot here, the region which is here indicates that the asphalt is too soft. That means the temperature is extremely high, viscosity is very low. So, asphalt is too soft in that condition, and because of that you get high temperature issues like rutting and bleeding, quite commonly seen in India, right. We see a lot of this in India, rutting and bleeding, because temperatures can be quite high, leading to the flowability of the asphalt. If you go to very cold climates, when the temperature becomes extremely low, asphalt gets extremely brittle. Just like any other polymer, asphalt also gets very brittle at low temperatures, and because of that you get the problems of low temperature thermal cracking. So, for every type of the asphalt binder, there is an optimum range of viscosity that defines the range of temperatures in which the asphalt will be giving the desired performance. So, you need to ensure that you build your pavement with the right idea about the material. So, this means that you need to have some basic understanding or characterization of the raw material itself, the asphalt itself, to try and understand what are the working temperatures in which this can actually make the right kind of properties. The other major challenge with asphalt, apart from temperature, is also the fact that asphalt is not just a homogeneous material. Like we look at it, we look at a black gooey substance, it looks quite homogeneous, but in reality it is also quite heterogeneous, not as heterogeneous as concrete perhaps, but you have some heterogeneity here also. It is a multi-constituent material, it has got the solid phases asphaltene and the liquid phase petroleum that are intermingled. Okay. So, again if you look at the definition given by the Strategic Highway Research Program, asphalt is a mixture of strong and weak acids, strong and weak bases, neutrals and amphoterics. So, you have several different kinds of chemical species inside the asphalt. Okay. And then again there is petroleum industry gives you different schemes of actually classification of fractionation of the materials of the constituents of the asphalt. Okay. So, multi-constituent nature is one thing. We already talked about temperature, but just to give you some idea about the specific characteristics of asphalt that we have to look at very carefully. So, asphalt behaves in a very transitory manner between -40 and 100 degrees Celsius. Now, of course, you can imagine that much of this is in the range of working temperatures in most parts of the world, right. There are parts of the world that go down to -40, there are parts of the world that go up to 55 degrees Celsius ambient temperature. Since asphalt is black, it will absorb a lot of heat, and the actual temperature in the asphalt may actually reach up to 80, 90, probably even 100 degrees Celsius. So, within this temperature range, you have so many different transformations that actually occur within the asphalt. So, at very low temperatures, asphalt is brittle, so it is a glassy solid. You increase the temperature, it becomes highly viscoelastic, but it still remains a solid, and that is what we see in the actual pavements that are functioning outside. But when you take it to a slightly higher temperature, it transforms to viscoelastic fluid, it starts moving, and then finally when you increase the temperature to about 100 degrees Celsius, it becomes a Newtonian fluid. That means it has absolutely got no inbuilt shear resistance, it can continue to flow continuously. So, according to Claudy, the thermal events of asphalt include below 0 degrees Celsius, there is glass transition. What is glass transition? It is nothing but this transition from the glassy solid to the viscoelastic solid. It happens at a temperature below 0 degrees Celsius. Between 0 and 90, there is a gradual dissolution of crystallized fractions. So, when your crystallized fractions start dissolving, your material becomes more and more fluidy, right, it starts flowing. So, that is where you start seeing this transition, and finally, above 100 asphalt behaves like a homogeneous solution, which is similar to that of a Newtonian fluid. Okay. So, you need to understand that the temperature of testing will be very critical as far as asphalt concrete is concerned, like any other polymer for that matter. The internal structure of the asphalt also keeps evolving with time, right. So, there is some molecular structuring that can take place inside that leads to internal structure evolving with time. We think that it is only cement when it hydrates with water, it continues to react until we cure the concrete, and that keeps changing the internal structure of the cement paste. But the structural changes that can happen in polymers and asphalt in particular can also be sometimes irreversible. They can keep, the structure can keep changing, because of which the characteristics also keep changing. So, that is why characterization of this material becomes extremely important. So, again asphalt concrete is just the level of sophistication that we get from Portland cement concrete. Instead of Portland cement and water as the binding medium, here you have asphalt as a binding medium. Okay. And unlike concrete, which mainly gets its strength from the bond between the paste and the aggregate, here the strength is primarily derived out of aggregate interlock, and because of that, or stability and strength are derived primarily out of the aggregate interlock. Because of that, aggregate gradation is very important, and you need to ensure that the aggregate gradation is chosen carefully, so that you get the best stability of the pavement. Now, there are certain characteristics that you desire from asphalt concrete pavements. Obviously, stability is the most important characteristic. There should be resistance to permanent deformation, because you have vehicular load which is continuously moving on the structure. And because there is a continuous type of movement, there is also fatigue that comes into place. So, fatigue resistance is also a very important characteristic of asphalt pavements. Thermal cracking at low temperatures, we saw that when asphalt becomes too brittle, you get thermal cracking. So, it should be resistant to thermal cracking. There is resistance to aging or hardening during production in the mixing plant and in service. Like any other polymer, when you expose it to external environment, to moisture, to ultraviolet radiation from the sun, the polymer properties keep changing. So, that is basically called aging, and with aging asphalt starts losing its flexibility, right, and because of that you may have some problems during service. Then there is resistance to moisture induced damage, such as the loss of bond between aggregates and asphalt. That could be a very important problem to deal with, especially during the rainy seasons, right. And then there are other rideability related parameters like skid resistance and so on, and the workability of the material itself at the point of time of placing the asphalt concrete. So, these are characteristics that need to be designed for when you design the asphalt concrete mixture. Of course, you have all seen this before, that asphalt concrete forms generally the top two layers of flexible pavement, right, and the bottom layers are essentially composed first of a granular course, which is basically the base course, and then you have the sub base and followed by a compacted soil layer. So, this is just for rekindling your memory on pavements. You all know very well about flexible pavements and the design of flexible pavements, but probably you may not have paid that much attention to the structure of the asphalt concrete itself, which needs to be different for the two layers that are there. First is the surface layer, and then you have the binder layer. So, you need to choose your aggregate sizes sufficiently well, so that the surface layer gives you a dense, impermeable and smooth characteristic, whereas the binder layer is where the maximum part of the asphalt concrete is, and that is really responsible for your strength and stability of the pavement. So, the binder layer keeps the pavement stable, whereas the surface layer primarily is responsible for the rideability characteristics as well as the resistance to moisture penetration and so on. So, there are several modes with which an asphalt pavement can fail. You have rutting, which happens when there is high temperature, and because of which there is permanent accumulation of deformation right under the path of the wheel, right. You would have seen this in many pavements. Okay. Fatigue cracking happens because of repeated bending of the asphalt layer, and then you have thermal cracking because of brittleness at low temperatures. You could get excessive roughness of the pavement surface that causes a loss of rideability conditions. Okay. And then you also have bleeding or flushing. When the asphalt becomes extremely fluid, it starts coming out and settles on the top surface as pools. Okay. So, that is basically called bleeding in high temperatures. Raveling associates with the loss of flexibility of the asphalt because of aging and oxidation. So, essentially your pavement is not as flexible as it used to be before, or material is not as flexible, because of which it starts cracking. Then stripping is the loss of bond between aggregate and asphalt that happens because of moisture intruding into the pavement. Now again, because of all these difficulties that we discussed earlier, you can add to those difficulties with this non-linear viscoelastic nature of asphalt concrete. Now non-linear itself means there is a lot of issues to deal with when you actually start modeling the material, and characterizing the properties to do that modeling can become quite a bit of a challenge with non-linear materials. Something like glass, something like chalk, it has got a linear brittle sort of a relationship, but in asphalt we have a non-linear viscoelastic nature. Okay. So, there is, with loading you not only have the elastic response, you also have a viscous response just like other polymers. So, because of this viscoelasticity exhibited by asphalt, apart from temperature, the other characteristic that determines the response of asphalt concrete is the rate of loading. Okay. Of course, in cement concrete also we choose certain specific rates of loading when we do our characterization test like compressive or flexural strength, but there the rate of loading does not have as big of an influence as it does with polymeric materials, especially with asphalt concrete. So, here rate of loading has to be very specifically maintained to ensure that we get consistent results each time. And of course, internal structure, the asphalt concrete can also change. We talked earlier about modification of the structure of asphalt itself, but asphalt concrete can also change its internal structure. How does it do that? If you think of it, asphalt concrete is a mixture of asphalt and aggregate, and obviously you can't have a system that is free from voids, there will be voids inside the system. Okay. So, for example, here you have these active aggregate particles and you have the spaces in between that are the voids. Okay. So, these voids can keep changing with time. Air voids basically reduce from 8 to 10% at the beginning to about 3 to 5% in approximately 5 years. So, when your air void system is evolving in this inside the composite material, obviously the properties also will change. So, structure evolves with time, and it is important to characterize the air voids, and this will influence the rutting behavior and also resistance to fatigue cracking. Right. Fatigue resistance increases as the load repetition increases. Now, that seems to be contradictory, but that happens because you have now lesser voids in the system. As you have more load repetitions, the structure gets more and more compacted. Then of course, there are other issues also with the internal structure, like rearrangement of the positions of the aggregate if the gradation is not proper and so on, and then you have a complete volumetric change that can lead to different types of properties exhibited by the asphalt concrete, unlike what you started off with in the initial stages. Okay. So, with cement concrete and asphalt concrete, the primary things that we were concerned with were the time dependent deformations. With metals like steel, time dependent deformations are not such a great concern. Creep, for example, with metals is almost minimal as compared to something like concrete or asphalt concrete. So, with metals, the elastic characteristics or load responses, temperature responses are a lot more crucial as compared to your long term loading or sustained loading type performance. So, let us look a little bit about steel. You know very well that steel is obtained from this very well controlled process, where first you have the blast furnace where the pig iron is produced, and then you have further purification of or removal of the carbon content from the pig iron to actually get you the molten steel, and molten steel is cast into various shapes and types of steel rolls. Okay. So, what we are primarily concerned with as civil engineers obviously are structural shapes, rails and bars. Okay. Of course, all these other things also find use in some aspect or the other of civil engineering, but most of the times we are dealing with structural sections with steel which are used directly for steel construction. Rails are obviously important for transportation network, and bars, rounded bars of steel are used for reinforcement in concrete. So, that is primarily what we are concerned with. Now, steel itself may appear to be homogeneous at the macro level, but at the micro level it has got a different type of microstructure exhibited at different temperatures. At room temperature, the stable form of pure iron, that means without any carbon in it, is alpha iron of ferrite, and that has got a body centered cubic structure. Okay, you will learn a little bit more about crystal structures later when you actually undergo the chapter on X-ray diffraction, but body centered cubic specifically means that you have atoms at the cubical corners and one atom right in the center of the cube, if you consider a single cubic unit cell. Okay. But then when you increase the temperature to more than 912 degrees Celsius, this ferrite, which is pure alpha ion, is transformed into austenite or gamma ion. Okay. Now, when you process steel, it is actually a mixture of iron and carbon. Okay. You actually mix iron and carbon, because pure iron is too ductile and very soft. You do not want that kind of characteristics from steel. You need higher strength, you need some degree of hardness, but you also need ductility. So, that hardness is introduced in steel by the incorporation of carbon. Of course, if you incorporate too much carbon, the steel becomes too hard and too brittle, and that is not suitable for structural applications. So, we actually have very small limited intrusions of carbon into steel. So, when you start mixing two solid phases and do a time temperature transformation, you result in what are known as phase diagrams. So, essentially you need to study the phase diagram between iron and carbon, which are the two constituents or components in the iron carbon mixture that we describe as steel. And the relevant portion of the iron carbon phase diagram, which corresponds to most types of steel and iron that are used in practice, are till about 6.7% weight percentage of carbon. Okay. Please remember, there are atomic percentages and weight percentages. Atomic percentage means if I have a formula, let us say of NaCl, the atomic percentage of sodium and chlorine is 50% each. But the weight percent of 1 mole of NaCl will depend on the relative molecular weights of sodium and chlorine. Okay. So, the weight percent has to be calculated that way, but the atomic percentage is calculated directly from the chemical formula. So, this is 6.7 weight percent of carbon, okay, which actually transforms to the chemical formula Fe3C, and this material is called cementite. So, at 0 you have ferrite, at 0% carbon, or at very low percentage of carbon you have ferrite, and when you go towards 6.7 carbon you have cementite. So, all the relevant iron carbon phase diagrams that you see in textbooks will be between 0 and 6.7 from the ferrite phase to the cementite phase. Carbon, so if you look at the macro level, steel looks homogeneous. At the micro level, the heterogeneity is introduced by carbon, which is an interstitial impurity in the iron and forms solid solutions with the forms of iron. What is a solid solution? What is a solution? When one material is dissolved into the other, right. Typically we think of a solid dissolved in a liquid, but when a solid dissolves into a solid, we call it a solid solution. Okay. In metals, many phases form because of solids dissolving into other solids. Okay. So, if you look at this iron carbon phase diagram, there are very specific points of interest. Okay. For example, I said earlier that you start from 0 to 6.7 weight percent carbon. At 0 you have alpha phase or ferrite, and at 6.7% carbon you have cementite or Fe3C phase. Okay. If you look at the diagram in between these two phases, you have different types of structures exhibited or different types of phases exhibited with different carbon contents, right. So, as I said earlier, you are interested primarily in very low carbon contents to ensure that you have the sufficient blend of strength and ductility introduced into the steel. In most cases, as far as steel for structural systems is concerned, we are dealing with carbon contents which are extremely low. Okay. Now, for tools, for the workshop and for machine shops, they need extremely high hardness from the tools, because this tool has to wear out the other metals which are getting ground, right. Those tools will have a higher carbon content. The tools will have higher carbon content. You do not need ductility from the tools, you need greater amount of strength and hardness. Okay. So, as you increase the carbon content, what happens to the strength? Increases. But what happens to ductility? Ductility decreases. Okay. So, in general, for most materials, that is one compromise that you will have to make. Whenever you increase the strength, generally you reduce the ductility of the material. With any material, let it be cement concrete, asphalt concrete, steel, polymer, whatever it is, the higher the strength, the lower the ductility. So, nevertheless, what we are talking about here is the region of the phase diagram that is corresponding to extremely low percentages of carbon. So, that means that is below this certain composition of iron carbon phase diagram, which is marked as the eutectoid transformation. Now, eutectoid transformation happens at 0.77% carbon content, 0.77% carbon content. So, if you take an iron carbon mixture with 0.77 percentage carbon content and you heat it to a temperature that is above this eutectoid temperature or 727 degrees Celsius, if you heat it to a temperature above that, it becomes entirely the gamma phase, austenite phase, which as we saw earlier had an FCC structure, phase centered cubic structure. When you start reducing the temperature from here and when it crosses this 727 degrees Celsius, when the temperature gets below 727 degrees Celsius, this gamma phase gets completely transformed into a mixture of ferrite phase and cementite phase. So, one solid phase gets transformed into a mixture of two other solid phases, ferrite phase and cementite phase. See, we started off with components iron and carbon, but now we have phases because they have intermingled and mixed together. Because of that you get phases. Okay. The phases that you get is alpha and cementite phase. And if you look at the microstructure of this phase under the microscope, you will see that it looks like something which is known as the mother of pearl. That is why it is given the name pearlite. Okay, it resembles a structure known as mother of pearl, and that is why it is called pearlite structure. So, at 0.77%, which is known as the eutectoid transformation, one solid into two other solids, at that temperature austenite converts completely into a mixture of alpha and Fe3C. Okay. There is also one more transformation point which is given here, that is eutectic transformation. Eutectic transformation involves the transfer of one liquid phase into a mixture of two solid phases. So, what is the difference between eutectoid and eutectic? Eutectic means one liquid to two solids, eutectoid is one solid to two solids. Okay. But we are not really worried about this portion of the diagram because we will never go so high in carbon content as far as structural steel is concerned. We are primarily dealing with this low carbon content. Typically, your mild steel will have carbon content of less than 0.2%, typically less than 0.2%.